In this video, I'll explain how to compute the effective electrical conductivity of a material using the PuMA software. It's assumed that the installation has been complete. If that's the case, then PuMA can be run by simply typing PuMA into any terminal. Once the window appears, the first step to compute the effective electrical conductivity is to import a 3D Tiff file or generate an artificial geometry. In this case, we'll generate an artificial geometry and we'll make it a carbon fiber material. So in this case, we'll use, say, 256 cubed with a radius of 5 plus or minus 0 and a length of 50 plus or minus 0, and we'll make it, actually let's make it transverse isotropic, so 90-degree variation in the x and y direction and 15-degree variation in the z direction with a porosity of 0.7. The next step is to go to Material Properties, Conductivity, Finite Difference, and then select Electrical Conductivity. We define the two material phases. Since this is an artificial material, the cutoff value is 128, which means that the void phase is defined as between 0 and 127. And we'll assign an arbitrary value for the local electrical conductivity. The solid is then defined as 128 to 255, and we'll define the value of 10 for the electrical conductivity of the carbon fibers. The accuracy is defined as the value the value at which the residual reaches for the iterative solver that the iterative solver will stop and say it's reached a close enough approximation. This value is typically taken to be to the minus 1e to the minus 4. For slightly less accuracy and a little bit quicker, you can use 1e to the minus 3 and 1e to the minus 5 or 6 if it's a little bit more accuracy is wanted. But typically 1e to the minus 4 will get you a very accurate solution. And then finally the number of threads, which is typically taken to be 4. I'm sorry, not 4. It's typically taken to be the number of physical cores on the machine, in this case 4. The simulation directions are checked. In this case, we'll run it in the x direction, y direction, and z direction. Since it's a transverse isotropic material, we should get different values for the z direction than we would in the x and y direction. And finally, the save resulting map. Now, what this will do in the case of electrical conductivity is it will save the steady state voltage potential at every point, and it will save the steady state current flow in through the material at every point as well. This will be saved under the runs folder in conductivity maps. So in this case, nothing is there yet, but there will be once the simulation progresses. To start the simulation, click Begin Simulation. And one thing I hadn't discussed, which I'll talk about while this simulation is running, is the domain size impact on the speed of the electrical conductivity solver. The electrical conductivity uses the same solver as the thermal conductivity, which means that it's based on a fast Fourier transform for part of it. The fast Fourier transform is the speed of which is dependent on the size of the domain. It tends to be fastest for domain sizes of 2 to the n, which is why we chose a sample size of 256 cubed in this case. It doesn't have to be 2 to the n. For example, 400 or 800 or 1,000 cubed works fine. The main thing is that you want to minimize the size of the largest prime factor. So 2 to the n plus 1 or 2 to the n minus 1 typically results in a very, very slow computation. It can be an order of magnitude slower than simply 2 to the n. As you can see here, the simulation's finished. Actually finished in very few iterations. That's in large part due to the fact that there's not that much contrast that we assigned since we just chose arbitrary values between the air and the carbon fibers. But the effective electrical conductivity is then shown here, 2.5 in the x and y direction, which is to be expected since it's a transverse isotropic material. These two should be the same. And since we assigned a different value for the angle variation in this direction, as you can see here, the carbon fibers have a preferential direction. They have less variation in the z direction in terms of angle So we would expect a different value here, and that is what in fact we see. We see about 1.9 for the value there. And as you can see here, the values for the steady state current and the values for the steady state voltage potential have been saved in the conductivity maps section of the PuMA run folder. And that concludes the effective electrical conductivity aspect of the PuMA software. I didn't get into all the details here. There's more of the theory described in the user manual as well. So if anything remains unclear, I recommend that you go read the user manual in this section.